Good morning, students. Today we are going to discuss about the user mode rootkits. User mode rootkits are a type of malware which is designed to gain unauthorized access to a system while remaining undetected. It is not detected by the administrator. Unlike kernel mode rootkits, which operate at the kernel level, this will manipulate the core system functions, and the user mode rootkits operate in user space, interacting primarily with applications and processes. Malware, they often go to great length to hide its running process and persistence mechanism from the user. The most common tool used to hide malicious activity is referred to as a rootkit. Already we discussed in Unit 1. The rootkits can come in many forms, but most of them work by modifying the internal functionality of the operating system. These modifications may cause files to be hidden, then processes, network connection, or other resources to be invisible to other programs, which makes it difficult for the antivirus products, administrators, and security analysts to discover the malicious activity. Some rootkits they modify user space application, but the majority modify the kernel since protection mechanism such as intrusion prevention system are installed and running at the kernel level. Both the rootkit and the defensive mechanism are more effective when they run at the kernel level rather than at the user level. At the kernel level, rootkits can corrupt the system more easily than at the user level. The functionality of user mode rootkits. Hiding its presence. The user mode rootkits can conceal files, processes, and network connections from the user and the security software, which makes it difficult to detect their presence. Manipulating the APIs. The user mode rootkits often hook or modify the API calls to intercept and alter the data returned to any application, which in turn helps them to hide activities or present false information. Process injection. The user mode rootkits may inject malicious code into legitimate processes, which in turn allowing them to run stealthily and leverage the permission of those processes. And they may gain control over applications by manipulating the application to perform unauthorized actions such as capturing keystroke, taking screenshot, or exfiltrating the sensitive data. Techniques for covering the tracks. File hiding. So user mode rootkits can change the file attributes or use file system tricks to hide their own files or those of other malware, preventing them from being easily discovered. So it is very difficult for the administrator to trace the user mode rootkits. Process hiding. By hooking system calls related to process enumeration, the user mode rootkits can make their processes invisible to standard system tools like the task manager. So the task manager will not list out the user mode rootkit process. Network traffic obfuscation. So the rootkits may imitate or discuss or alter the network traffic, allowing them to communicate with command and control servers without detection. Registry manipulation. The user mode rootkits can modify the registry entries to hide their presence or disable security features such as antivirus software. API hooking. They often hook into functions which return the system information like create file, enum processes, etc. to filter out their own process or files from being listed. So detection and mitigation strategies of user mode rootkits. Behavioral analysis. So instead of relying solely on the signature-based detection technique, using behavior-based detection methods will help identify anomalies uh, caused by the user mode rootkits. Integrity monitoring. Tools used for checking the unauthorized changes to files, processes, and registry entries will be used to, which will help to detect the presence of the rootkits. Then regularly performing the system audits by checking the system activity, file integrity, and network traffic which will help the administrator to identify the unusual behavior which might indicate a rootkit infection. Use of specialized tools. There are specific rootkit detection tools. Example, rootkit revealer, GMER. These are the tools designed to identify the presence of the user mode rootkits. Then, by best practicing safe computing practices, that is, educating the users about safe browsing habits, avoiding suspicious downloads, and maintaining updated antivirus software, which will help prevent infections from user mode rootkits. Import address table hooking, that is IAT hooking. It is a technique used by the malware and sometimes by the legitimate software to intercept function calls made by an application to external libraries such as DLLs, dynamic link libraries. This method allows the attacker to modify the behavior of an application by redirecting the function calls to their own code, enabling different types of malicious activities while keeping the original application functionalities intact. IAT hooking. So it is a classic user space rootkit method which hides files, processes, or network connections on the local system. This hooking method modifies the import address table, that is IAT, or the export address table, EAT. So an example of IAT hooking is shown here in the figure. It is a legitimate program calls the terminate process function, okay, which is mentioned as call one in the left hand side under legitimate program. Normally, the code will use the IAT to access the target function in kernel 32.dll. But if an IAT hook is installed as indicated at call number 2, okay, so the call number, that is the malicious rootkit code, will be called instead. That is, it is available in the center side IAT with the hook. That is second dark line rootkit code. That is the second call, which will invoke the malicious rootkit code. Then the rootkit code returns to the legitimate program to allow the terminate process function to execute after manipulating it with some parameters. So in this example, the IAT hook prevents the legitimate program from terminating the process. So the rootkit is here inserted at the last right side of the diagram. You see rootkit is inserted with malicious code in the by capturing the address at the IAT with the hook, second line. Okay, so the IAT technique is an old and easily detectable form of hooking. So many modern rootkits use the more advanced inline hooking method instead. Generally, how IAT hooking works. Understanding the IAT. So when an application loads, it has an import address table which lists the addresses of functions from the DLL that the application uses. This table allows the application to call functions without needing to know their location in memory ahead of time. The hooking process. The attacker or a legitimate program can modify the entries in the IAT to point to a different function instead of the intended one. This may involve loading the target application, then identifying the function in the IAT that needs to be hooked, then replacing the address in the IAT with the address of the malicious function that already we have discussed in the previous example. Execution. Finally, the application calls the hooked function. It instead calls the attacker function, which can execute the malicious action while potentially calling the original function as needed in order to maintain the functionality. So example scenario. So it will targeting a function. Suppose a malware developer wants to hook the create file function to log all the file access, because the create file will create a new file. It will log whatever credentials used by the users in the network. It will store all the details, and that can be hacked by the malware attacker. Modify the IAT. The malware replaces the address of the original create file function in the IAT with the address of its own logging function. Then logging activity. Whenever the application calls the create file, then the malicious function executes the logging the file access before optionally calling the original create file function to perform the actual file operation. So detection and prevention. How IAT hooking can be detected and prevented by performing this integrating checking, that is implementing checksums or hashes, computing hashes. Hash is nothing but a fixed message size digest generated by either MD5 algorithm, message digest by algorithm, or secure hash algorithm SHA with different versions. And these hashes are attached with the original text and sent through the email for security purposes. And this checksum and hashes for the IAT entries can help detect unauthorized modification, behavioral analysis, monitoring the application for unusual behavior or unexpected function calls can help identify potential hooking. Anti-malware solution uses advanced security solution which can detect and block hooking techniques. And finally, code signing. It is a method which ensures that all DLLs and executables are signed, which helps to identify the unauthorized modifications. Inline hooking. So it is a technique which is used to intercept and modify the execution flow of a program at runtime by replacing a portion of its code with a jump instruction that redirects to the custom code. This technique is commonly employed in both malware and legitimate software for various purposes, including monitoring, debugging, and modifying the application behavior. Inline hooking overrides the API function code contained in the imported DLLs. So it has to wait until the DLL is loaded to begin executing. IAT hooking simply modifies the pointers, but inline hooking changes the actual function code. A malicious rootkit performing the inline hooking will often replace the start of the code with a jump that takes the execution to malicious code inserted by the rootkit. In other ways, the rootkit can alter the code of the function to damage or change it, rather than jumping to the malicious code. In general, we'll see how inline hooking works. First, it will identify the target function. The first step in inline hooking is to identify the function, the target application that the malicious attacker want to intercept. This function could be an API call or any internal function. Modifying the code. The hooker replaces the first few bytes of the target function with a jump instruction. It is often called a hook. And this jump instruction redirects the execution to the custom code, the hook. Then by executing the custom code can perform its own operations, that is example logging, modifying the parameters, and then optionally they call the original function to maintain normal functionality. Then restoring the control. After executing the custom code, the control will return to the original function. In turn, it allows the program to continue as intended. It may involve saving the original bytes that were replaced and restored after the hook executes. Inline hooking example. So the example of the inline hooking of ZW device IO control file function is shown here. This function is used by program like netstat to retrieve the network information from the system. So in this program, the ZW device IO input output control file is moved to the ADI file, that is data file, and then the location of the function being hooked is acquired at 1, that is get process address call. And this rootkit goal is to install a 7-byte inline hook at the start of the ZW device IO control file function in the memory. This table shows the byte inline hook that was initialized, and the raw bytes are shown on the left. So left side you can see the raw bytes, and the assembly is shown on the right. So the raw bytes are disassembled by the hook, inline hook. The assembly starts with the opcode 0xb8, that is move immediate read instruction, followed by 4 0 bytes. Okay, then the opcode OXFF, OXE0, jump EAX, second statement. The rootkit will fill in these 0 bytes with an address before it installs the hook. so that the jump instruction will be valid. So now you can activate this view by pressing the C key on the keyboard in Idea Pro. The rootkit uses a simple memory copy, that is mem copy, that is in the second program, mem copy to patch the 0 bytes to include the address of its hooking function, which hides the traffic destined for port number 443. The address given, that is the last one, 0004011, okay, which is highlighted in the table byte inline hook, second line. Okay, so it matches the address of the 0 bytes in the previous example. The patch bytes, that is 1004010, and the hook location are then sent to a function which installs the inline hook. So this is a screenshot showing how the inline hook is installed. And now the ZW device IO control file will call the rootkit function first. Then the rootkit hooking function removes all the traffic destined for port number 443, and then it calls the real ZW device IO control file. So everything continues to operate before the hook was installed. Since many defense programs expect inline hooks to be installed at the beginning of functions, many of the malware authors have attempted to insert the jump code JMP or the code modification further into the API code to make it harder to find. So where it is actually present. So finally the call install inline hook will call and it modifies the data. So the detection and mitigation strategies. The inline hooks can be detected by doing integrity checking. Regularly checking the integrity of critical application functions and memory can help detect unauthorized modification. Then behavioral monitoring. So by checking the behavior of the applications for unusual behaviors or any unexpected calls, which help identify the presence of inline hooks. Then the users or administrator has to employ endpoint protection solution or advanced security solution or tools which can detect and prevent the hooking techniques. Code signing, and we have to ensure that all executables, exe files and library files are designed to verify their integrity and prevent any unauthorized modification. So inline hooking is a powerful technique that can be utilized for both beneficial and malicious purposes, and we should understand how it works, and its application and methods for detection and mitigation is essential for maintaining the system integrity and security. We have to employ best practices, and using appropriate security measures, the organization can protect themselves from the risk associated with inline hooking. This is the reference. Thank you.